see it. Okay, normally it just starts wherever it needs to start. So, hello. Normally it starts from the beginning, and I don't think it skips anything from the beginning. But yeah, hello everybody. Welcome to today's stream. Oh, I forgot the music. Look at me go. Okay, welcome to today's stream. Today I am joining you from the hyperbolic time chamber. Because today we're getting in some training we're getting in some training in. What am I saying? We're getting some training in. Yeah, that's what I meant to say. We're getting ripped. We're getting our brains ripped. And we're getting all of these algorithms and data structure patterns ingrained in our brains so we can ace those technical interviews. We're training some LeetCode today. So yeah, we'll follow from where we left off on Monday. And we're just gonna solve a couple problems. I'm gonna run through my approach, and yeah, we're just gonna enjoy the process and learn a little bit. So, okay, updates about my life. I had. Oh, once again, I should preface before I start talking about work. Once again, disclaimer, it's in the description. I'll say it just because I'm talking about work. All of the views expressed here in this stream are my own. They don't represent my employer, SOTI, and LeetCode University in any sort of way, shape, or form. Now, with that being said, updates from work. So it's been a month and like a week since I joined SOTI as an associate software developer. And I've been working in broad terms in like a project about evaluating LLMs. And like yesterday, basically the whole project kind of turned on its head a little bit. We had I had a meeting. Let me turn down this music maybe. That didn't help. Okay. I had a meeting with management, and the whole it's not changing that much. Maybe I'm exaggerating, but the scope of the project is changing a little bit. So we're gonna have to rethink some stuff, but I think this is good. This is good practice. I mean, it's good and bad. I don't think it's bad, but it has its ups and its downs. In that, I mean, downs is like we're gonna have to rethink the approach. We can't just keep doing what we're doing. But in the good part is I get exposure. Okay, maybe turn it up a little bit. I get exposure to like a little bit more corporate life, because before in my previous workplace it was like small departments, so things like this didn't happen. Everybody was very closely connected to the projects I was working on, so like updates were really fast and I was mostly leading them. So from like a general perspective, there might have been places where stakeholders like disagreed with me, but for the most part I was the technical lead and I could take the project in the direction I thought would be best. But now that I'm in like a bigger company, there's like some checks and balances that happen with projects, and like there's like chains of management, so that kind of works a little bit differently. So getting exposed to that is good, and being able to pivot from ideas, I think it's a good practice. And overall, I think the direction where this project is shaping to go is still I think it's still good. I think it's still worth it. And it just kind of gives some teachings for the future on how to like handle progress updates and that sort of stuff. But yeah, it's a little bit about work. I mean, we talked yesterday. Has there happened anything happened since then? Not really. Oh, I started watching X-Men 97 because my roommate just finished season 1, so he caught up with me, and so we started season 2. Shout out to Jaden. I don't know if he's watching. And it's good. It's good. I didn't remember like I didn't remember how much happened in the first season. I feel like there was so many different like different arcs that happened in the first season. Um, but yeah, it's kind of exciting to start again. It's a good show, honestly, very well produced, and like I know it's mostly like they're not really like creating anything new. Like all the stories are written in the comics, but still, I think it's a fun implementation, like a fun iteration of the show. Okay, I think that's enough talking. I think people have had time to join in. Um, let's dive into my little bit of a warm up, which is the Lurkana card of the day. Okay, from set two. This is Peter Pan's Dagger. It's a 2-cost uninkable. Uninkable means you can't put this in your pool of resources. You have to play it as a card or get rid of it in some way. Like you can discard or whatever, but you can't really use it for anything other than its intended purpose. Because with cards that have like a little ring, a yellow ring around them, that means you can use them. If like you can't use them at the moment, you're gonna have to wait a lot of turns. You can just use them as resources. You can just put them in your resource pool, and like they don't get their intended effect, but that means you can use them immediately. They get instant value to you, and they become resources so you can play your other cards. With this one, you can't do that, so you have to play it as in like its intended effect. And it's called, so it gives you a little bit less flexibility in that sense. It's called Peter Pan's Dagger. It's a 2-cost uninkable. It's an item card. And it says your characters with evasive get +1 strength. Like so much other lore, Peter Pan's dagger was safe in the Great Illuminary until the flood. The artist, if you see right here, it's Leonardo Giamicelli. It's card 135 out of 204 from set 2 in English. It's an uncommon, and well, just the same thing that it says in this corner. Review of this card. This sucks. Like truly sucks. So, a little bit of an overview of like what items are in Lorcana. Um, items. So like with, okay, so there's 3 different types of cards in Lorcana. I mean, there's more like subtypes, but 3 main types. There is characters, there is items, and there is actions. Characters is what you'd expect in like from even from like other TCGs. It's you play them, and then they stay on the field until they're banished. I'm not gonna say killed, or they're like put away from the field in some other way. They return to your hand, whatever. They stay in there. They can challenge or attack other characters. They can quest for lore, which gives you points towards your end goal, which is to get 20 points, 20 lore. They can quest for lore. And they can do other stuff like sing songs and stuff like that, and they have effects. But its main purpose is to be on the field and gain you points, and then challenge other characters so that your opponent doesn't gain points. Actions. It's kind of like a one-time effect. It's like a spell in Yu-Gi-Oh or in other TCGs. I can't remember what they're called in Magic. I haven't really played Magic, so I don't know why I'm even trying. But basically, it's a one-time effect where you pay for a cost, you play it, and it gives you a one-time effect that does something. And items are oh, sorry, there's a 4th type, which are locations, but let's ignore locations for now. They don't really matter. Items, basically you play them for their cost, and they stay on the field until something removes them. And like that removal is not that common, so like they basically just stay on the field with their effects. They're not really like characters where you can't normally you can't gain points with them, and you can't challenge other characters with them, but they give you like effects um that can be good. Like you might be able to exert them for an effect or something like that. So this item, the intended purpose is you kind of like play it, it stays on your field, kind of like a continuous spell in Yu-Gi-Oh, and it gives your characters with evasive +1 strength. So this is bad because first it's uninkable, so you have to use it in this form. Second, it's only for evasive characters. which there are some like low cost evasive characters, and but in third it only gives you +1 strength. Okay, I can't with this music today. It's like some of it is really loud, some of it is really low. Like I don't know. So it's only +1 strength, right? And it doesn't give you any other value other than that, and you kind of have to play it as is. So it's not a lot of value for it. I don't see a reason why you would play this in your deck, especially since there's better cards that that also give your characters +1 strength. For example, I don't know what this guy's called, Candle something. Nope. Chandelier. Nope, that's a Pokemon. Candle guy in Beauty and the Beast. Lumiere, right. Lumiere. Like, this is just better. Like, so much better. I mean, it's set 4, like 2 sets after, so I guess at that point this... No, I don't think even at the point when this was released it was good. But it's in the same color, costs the same, but it's syncable, so it's flexible. You can use it as resources if you don't really have a use for it at the moment. It's a character, which means you can quest with it, you can attack with it, like you have more uses for it. And all of your other characters, not only the evasives, get +1 strength, +1 strength. So there's not really a reason for you to play this. Like, none. When you can just play 4 Lumieres. If you really need the +1 strength. Like, this is good, actually. This is good if you're playing, like, a strength-based, like, deck. But there's no reason for you to play it. So this card is horrendous. It might have been the worst card we've reviewed so far. Okay. With that said, let's go back to Grand 75. Actually, I should bookmark this. And then how do I show my bookmarks? Show bookmarks bar. So yeah, I don't want hacker rank. Do I really Google Translate? Nope, I don't need this here. I don't need this here. You know what? This might be nice to actually just open my, like, that account. I don't really need to open YouTube like that. I can delete this most likely. I can delete this most likely. Delete that, and I can pass that here. And I don't really need these groups anymore. Okay, sick. Let's see if this works. Nice. Okay. So, Grand 75. Go down the list. Core schedule. This is I really like this problem. Once again, I said this last time. I have not solved this problem in a long while, even though it says solved. Last time I solved it was November 2024. So, and I didn't look up a solution before I did this. I'm genuinely like solving it by myself. I do know this problem, and I might have read it before to get like a sense of what the problem is, but I didn't look up a solution or anything, just to start thinking about the problem. Okay. So, well, let's read the problem. It's problem 207 called Course Schedule. It says there are a total of num courses that you have to take, labeled from 0 to num courses -1. You are given an array of prerequisites where prerequisites AI, BI, indicates that you must take course BI first if you want to take course AI. So what does this mean? You get like an array like this, and so it says that the prerequisite for BI is AI. So you need to take AI before you take BI. Very simple. For example, the pair 0, 1 indicates that you must take course 0 to take course 1. Return true if you can finish all courses, otherwise return false. Let's see the example. So this example right here is there's 2 courses, and the prerequisites are that you must take 1 before 0. You can't finish it because you just take 1 and then 0. It's possible. This one, you have 2 courses. There's 2 courses, 0 and 1, and then the prerequisites are that you must take 1 before 0 and 0 before 1. You can't complete your courses because the prerequisite for 1 is 0, the prerequisite for 0 is 1. So you can't take either because you haven't completed either, and so it doesn't really work. Now, this is one of those problems that if you are not familiar with problem solving and we're doing LeetCode, it's gonna be a little bit hard to solve, or you're not gonna see the pattern at first until you start doing a lot of these types of problems. Until you start doing a lot of these types of problems, right? And so then you start identifying a pattern here, and that is, and they really kind of give it to you in example number 2. So what is very important here for this problem is that you need to define when can you not finish all the courses. And if you see here, that happens when, like in this 2 course example is very simple. It's whenever there is sort of like this loop, let's call it a loop for now, where you need one to start the other, and the other needs you to start like this is a prerequisite of this, and this is a prerequisite of this, so you can't take either. And there's no place where you can start and sort of like start completing your pre-requirements. There's this loop. Now let's give a more formal definition, and this is where we'll come to how what do we use to solve this problem. And the formal definition is it's like, I'm gonna just spoiler alert, this is a graph problem. So we're gonna define our courses as nodes in our graph. So let's say our num courses is num_c is equal to 2. We're gonna have 2 nodes, 0 and 1. And what are going to be our edges? Our edge is going to be directional first. This is going to be a directed graph. And an edge from 0 to 1 is going to mean that you need to take course 0 before you take course 1. Okay? You need to take course 0 is a prerequisite for 1. Now this is the, actually, if we go to like the first example, it says 1 is a prerequisite of 0. The edge would be this way, actually. Now, let's start with the example where you can't finish all your courses, which is this one. You need 1 to start 0, and you need 0 to start 1. Actually, let's draw it a little bit easier to see. Right? There's this loop we were talking about. In formal terms, there's a cycle in the graph. So when are we not going to be able to solve the problem? When there is a cycle in the graph. And we can see this not only with 2 problems. Let's say we have 3. Let's say we have 3 problems. There's now a problem number 2. Now you can have the like this problem like this, or even like this, right? So there is obviously like the same cycle we saw before. That is a problem in our graph. Why? Because, okay, if we start looking at this logically, you would first finish course 2 to unlock the requirements for 0 and 1. And then 0 and 1 now have 1 requirement each. The requirement of 0 is 1, and the requirement of 1 is 0. So you've reduced your graph to our previous problem, to num_c equals 2, and with the cycle we saw. Now let's see a less obvious example. What if we have something like this? Now, if we have something like this, it is still not, you're still not gonna be able to solve it, because why? To start 0, you need to complete 2. To complete 2, you need to complete 1, and to complete 1, you need to complete 0. So you can't start any of them because all of them have a prerequisite to each other. Now let's see an adversarial example, and that is something that looks very similar, but it's not, which is this. So in this example, you can complete all your courses, even though it's very similar to, like, if I did this, it would be the previous example and you can't complete it. But since it's this, you can't complete it. How? Well, you start the same. You start with course 2, and that removes the prerequisite for course 0 and course 1. Now, you can't start course 1 because you need the prerequisite course 0. But you can't start course 0 because you've already completed its only prerequisite, course 2. So you complete course 0, and now you remove this prerequisite. And then at the end, all the prerequisites for 1, which are 0 and 2, have been completed. So you can complete course 1, and then you're done. So we've reduced our problem to something, I guess, more like formally, simpler for programming. Because thinking about courses and schedules and prerequisites, it's hard to like translate into programming terms. However, this is easier because now we have a graph and we need to detect if there's a cycle. Now, I mean, depending on where you are in your development journey, you might know already an algorithm to detect a cycle. But if you don't, I'm going to teach you a very simple one, because that's the only thing we need to implement. We need to find a way to find if there's a cycle in a graph. Okay? And that simple algorithm is, I'm just gonna make it as simple as possible, and we're gonna run a DFS. This stands for depth first search, which I feel like I've done in the past. Maybe like, I think even like Monday's problem had some of this, but so in case you don't know, there's DFS is basically you start your search at any point in the graph, and then you visit the first edge you find. So like, okay, let me draw the previous graph I had. You start here, and then you go to 0. You go to 0 because it's the first edge you find. You're at 0, you go to 1. That's the first edge you found. There's no more edges here. Does that detect if there's a cycle? Yes, it should. Oh, yeah, because, okay. So you go as deep as possible, and then you explore all those possible paths, and then you return, and then explore all the remaining paths. So, like we were doing before, 2, you find the first possible cycle, which is this left one, let's say. And then we go to 0. From 0, we go to 1. There's no more paths, so we return to 0. There's no more paths at 0 to explore, so we return to 2. Now we explore this other edge. And then we find... and then we get to 1, and then we have no more edges to explore, and we're done. Right? I'm seeing a problem with the cycle detection thing. And it's that... And it's that we visit, so like the way I was gonna propose is, that you keep a dictionary or like a set of like the nodes you visited, and if you get to the same node again in a later iteration, then then that means you're in a cycle. But there's a problem with that. If we're doing the example where we do here, we go to 2, we put 2 and visit it. We go to 0, we put 0 and visit it. We go to 1, we put 1 and visit it. We go come back, visit this node. Oh, we're at 1 again. So there's a cycle, but there's actually no cycle in this. And that is because, right, so that is because it's not only that you visited it, it's that like in the current path you're going through, you haven't visited that node. I'll explain myself in a little bit. So basically, we're not only checking that we visited the node, we're checking that in the current path we're going through, how we already visited that node. So let's go back to our example of there being a cycle, which is this. So we keep this visited set. So we basically go 2, we visited 2, we go 0, we visited 0 in this current path we're going. I'm gonna start drawing it with red. So we've done this, and now we're gonna do this. So we visited 1, and then we go and visit 2, and now since we've already visited 2 in the current path, we started at 2, there is a cycle. Now let's go back to the previous example, which is this. Okay, we come here, we visit 2, then we go and visit 0. Then we go and visit 1, right? We put 1 in our visited. Now there's no more nodes to explore, so we backtrack. We do what's called backtracking. So we basically remove 1 from our visited because we're going back, and 1 is no longer in our current paths. And then we remove this red line as well, and now we only have visited 2 and 0. Then 0 has no other edges to visit, so we're gonna backtrack from that as well. We remove 0, we remove the line, and now we do have another line to visit here and another edge to visit here, and that is from 2 to 1. So now our path is 2 and 1, so we're gonna put 2 and 1, and when we get to 1, we see that 1 is no longer in the visited array, in the visited set. Even though it was before, it's not in our current path, so we don't need to worry about that. There is no cycle here since it's not in our, we didn't visit this node in our current path. We visited in a previous path, but we backtracked, so we don't need to worry about that previous run. So this is how we're gonna do it. Now there is one more thing, and that is thinking about graph problems. Nothing guarantees us that this graph is connected. And what do I mean by that? A connected graph means that you can, okay, I'm gonna show what a disconnected graph is first. This is a disconnected graph because you have like 2 different graphs that are not connected to each other. If I do this, this is now a connected graph because all of the graphs, like all of the nodes, are linked to each other by at least one edge, right? So technically, you can start from one of the nodes and you can get to other nodes in the same graph. If we have like this, if we just check these 3, we're not going to be able to find these 2. We have to go into these 2. However, if you have this, then if we go in 2, we're going to eventually be able to get to these 2. That's what a connected and disconnected graph means. So nothing guarantees us that this is a connected graph. And let's go back to the scheduling like vocabulary. And so what does it mean to be disconnected? It means Okay, let's make a simple example. A node could have no prerequisites. So it's going to have no edges, so it's going to be connected to nothing. It's going to be its own graph containing just one node and 0 edges. So this is a problem for our algorithm, because if you were thinking about just starting at one node and being able to visit the whole graph, you're not going to be able to do that. So you have to iterate over every single possible start node. You have to iterate over every single possible start node before you can determine if there's cycles in the graph. Because you could visit, like, you could start at 2 and visit this portion of the graph, but if, say, there is a cycle right here, you're not going to be able to notice by visiting just the 2 and this portion of the graph. You have to visit every single node. So to do this, we're gonna keep another set, a different set from, like, this is like the path set. This is the path set. We're gonna keep a scene set. And the scene set is gonna be all of the nodes we've seen so far. So when we, in this example, when we do our DFS and we start here, we're gonna basically visit 2, 0, and 1. And those are going to get added to our scene set. And then, so we start at, let's say we start at 0. No, sorry, we start at 2. Then we check how we seen 0. If so, don't like expand on that. Don't do a DFS from starting from there, because we've already explored all of the possible paths that could start at 0, because we've already run a DFS over it. Same with 1. Then when we get to 3, have we seen 3? No, we haven't. So we do need to run DFS here, and we run the algorithm. Okay? Let me know if you have any questions, because this is like a little bit hard to comprehend. If it's your first time seeing this type of problem, I can try to do a better job at explaining. Let's quit or exit. And now we're gonna go to LeetCode. Nope. Okay, and this is, like I mentioned, a graph problem, and this is problem 207, correct? Yeah. Graph/207.cpp. Nope. Okay. So, let's create our set. So set of, we're gonna say int. Scene and path, right? This is what we called it on the whiteboard. Ooh, there's another problem right here, and is we're not really given a graph. We're given a vector, like we're given the prerequisites like this. So we have to convert from this into our representation of a graph. So let's delete all of this. So we get a vector that has 0, 1 and 1, 0. So what does this mean? Okay. You can technically just use the array. Let's actually construct the graph. It's gonna make our program a little bit slower, but it doesn't matter, because it's just gonna make it easier for our understanding. And it's not gonna have that much time. So, what does this mean? So if we have 0 and 1, this means that 0 is the prerequisite of 1. So this means that there's an edge from 0 to 1. Same with this. This means that there's an edge from 1 to 0. Okay, that's all we need to know. That's how we're gonna construct our graph. To make it easier, we're gonna copy the implementation of a graph here. we're just gonna copy this. This is from the problem we solved on Monday that had like a graph. We're gonna use this as our implementation from a graph of a graph. So we're just gonna construct our graph. What was that problem? Let me just look it up again. That was update matrix. Number and click closest 0. Nope, that is not the neighbors. Right here. Clone graph. Okay, that's what that problem was. And for that, we're just given a node, and we were guaranteed that it was a connected node. Okay. So for this, we're gonna store our graph. You can technically represent this as an adjacency matrix or an adjacency list. Do I want to teach that today? Sure. Because I think this implementation of a graph is not common for LeetCode or competitive programming. You should know how to implement it in the most more efficient, you have to write less code way. Also, that is hard to remember. This, what I'm going to show you, is easier to remember. So another problem on top: how do we represent a graph in code? So one way to do it is like this, what they literally gave us, which is why I said you don't really need to convert the data that they gave you and any sort of other data, because this is already representing of a graph. You don't need any more information. For our purposes, we're going to make this a little bit easier to interpret. And so here, this is one way to represent a graph, which is a list of edges. The reason I'm going to propose to implement a graph is what I think is the standard for competitive programming, but I mean, there's multiple ways to do it. It's called an adjacency list, and you basically have a vector. So you have a vector of vectors. Okay, we're gonna write. So we have, let's say, our number of courses is going to be equal to, let's say, 5. So this is going to be our vector, and it's going to have, our outside vector is going to have 5 elements. So I'm just going to write the index for them here. So this is going to be index 0. This is going to be like course 0 or node 0. Node 1, node 2, node 3, and node 4. That's 5 elements. So these are just the indexes. And then in each of these, we're going to have another vector. And this vector is going to store all of the edges that are outbound from 0. What does that mean? All of the edges from 0 to another number. So if we start from this, there's an edge from 0 to 1. So here we're gonna store 1, and that's gonna be our full vector. In 1, there's an edge from 1 to 0, so we're gonna store 0. And let's say there's an edge from 2 to 4, and there's an edge from 3 to 1, and an edge from 4 to both 0 and 3. Let's draw this graph out to make it easier. So we have 0, 1, 2, 3, 4. So if we read this like this, so there's an edge outbound from 0 to 1. There's an edge outbound from 1 to 0. There's an edge outbound from 2 to 4. There's an edge outbound from 3 to 1. And there's an edge outbound from 4 to 0. And from 4 to 3. So this is our graph. That's how you read an adjacency list. Let's implement that. So we're gonna create a vector of int, and we're gonna call it adjacency list, and we are going to initialize it like this. It's gonna have num curses amount of elements, and each is gonna be initialized. Actually, we can just do this because it's just gonna initialize it with an empty vector, which is what we want. So that's our adjacency list. What we've created so far is this. Sorry. It's this. We created a vector with however many courses we have as positions and an empty vector for each of their edges. We haven't initialized their edges. Now let's go and initialize the edges. For prereq, a prereq is going to be a vector of int. Prereq in prerequisites. Int. We're gonna call them L and R, or I think it's normally U and B. Let's call it U and B. And these are it's just a standard in competitive programming to like name like nodes, basically U and V. So you have node U, you node V. I don't know why, but it's like I and O or I and J. Int U and V is equal to prereq. And now what we're gonna do is adjacency list U dot push back V. That's all we need to initialize our adjacency list. That's all we need. So now now we've initialized with all the edges. So from, let's say, from 0 to 1, the 3, this 4 and 2, and etc. etc. Now we need to run the DFS over this. And so for that, I'm gonna create a helper function, and it's gonna be called DFS. Actually, let's bool DFS maybe. Let's call it bool DFS, and bool DFS is gonna take this is I'm adding a lot of arguments to this thing. So we're gonna take our adjacency list. We're gonna take the current node, and we're also gonna take our set int of visited. So okay, we're gonna go over all of the edges. Okay, so first of all, we got to this node, so we're gonna say scene.add, I think insert, sorry. I think for sets it's insert. Scene.insert the current node, because this isn't the current path. Now that we've seen Oh, actually, this is path.insert. And we should actually initialize our scene set out here. Path.insert current node and scene.insert current node. So we've both seen and it's in the path our current node. Now let's look over every single edge starting from the current node. So for vector int edge from our adjacency list of our current node. So this is basically looking at all of the edges going out from our current node to other nodes. What do we do? Basically, we do if DFS of our adjacency list. Our current node is going to be actually yeah, it shouldn't be an edge, it should be out node, because we're accessing this vector and we're iterating over it. Yeah, so our current node is going to be the out node, and our scene is just going to be scene. So if this returns true, that means there is a cycle. That's how we're going to signal in this DFS. So if that returns true, just return true. Otherwise, just keep iterating over all the other neighbors. At the end, when we're done checking all of the possible like edges starting from the current node, we're gonna remove We're gonna remove the current node from our path. And let me see set operations in a sec. Set operations C++. Erase. So path.erase our current node, because we've explored this node fully. We're just gonna go back, and so for that we're removing the current node from our path. We're keeping it in scene because we have seen this node before, but we're removing it from our path. And then we're gonna return false because we didn't find any cycles in any of the edges going from this node outside. Okay, and now in here, what we're gonna do is, and like you technically don't need this scene set. It just helps with the efficiency of the problem. It helps you visit not visit edges that you have visited in the past. So we're gonna keep it because it just makes more sense. Now what we're gonna do is go over every edge. So for int I equals 0, I less than num curses, I plus. What we're gonna do here is we're gonna run we're gonna do the same thing we did here basically. Actually, oh, I see something here, and that says this is path. Our scene is out here, and so we have to make sure. So we don't have to create this here, but we have to make sure we do scene.clear every time we run this function, because tests reuse this function, so we want to clear the state from previous tests. So we create our set of path, and that's going to be empty when we first initialize it. And so if our DFS of our adjacency list starting at node I with our empty scene or set returns true, then we're gonna return true. And we go also here, before we even do this, we check if scene dot contains I like count. If scene dot count of I, then we're just gonna continue. What does this do here? If the current node we're trying to iterate over, we've iterated over it in the past, it's in our scene set, then don't explore it with DFS, just continue. Okay? And if not, if we have not explored it, then we're gonna explore it, starting from node I, as we see. And if that returns true, then we're gonna return true. Because there, the DFS indicated that there's a loop. Right? And then if we iterate over all of our possible nodes and we don't find any cycles, we're just gonna return false. Okay? So let's do this. Test. Cannot be declared with it has to be auto. Okay, right. C++ is not smart enough to figure that out. That's right here. Type vector in decomposes into one element, but two names were provided. Oh, right, so we don't even need to do this. Wait, no, I'm confused. Okay, no, it's even easier. Prereq 0 is gonna be here prereq 1. That's it. We're creating an edge from prereq 0 to prereq 1. Stack Overflow. So what this has given me, Stack Overflow means that our DFS just kept iterating and there's only these two examples. So it just kept going in a cycle. So, we forgot to include our condition to stop. So it's not only if we do this, but also if our out node is in our path already. If path.count our out node, or if DFS. So basically, if there's an edge from like the node where I'm right now to another node, and that node is already in my path, that means there's a cycle. If that doesn't happen, if there's not a clear cycle, if there's a cycle in the node I'm going to visit, then there's a cycle in the whole graph. Okay, so it's the other way around. You return true if you can finish all courses, otherwise return false. Okay, so this should be false, and this should be true, and this should be false, and this should be true. Now I have a problem here, and that is, why did this return true? this is true, return. Oh, if this is false, return false, otherwise return true. If this is false, then return false, otherwise return true. I'm sure there's another error here. And yeah, it's this. Now let's think why. There's only an edge from 0 to 1. Theme.insert path.count. Oh, what? The only thing I can. The only thing I can think of here is that we're not resetting our path outside here, but we shouldn't have to. I don't know if this makes a difference. Yeah, it does not. As I expected. If we've seen this continue, if it's not possible according to our DFS, return that. Erase core node, return true. Okay, we gotta figure out where is it saying no? So let's print our core node, I guess. Still debugging. So it's out in 0, if it's at 0, it's out in 1, it should be in the scene. Why did it go? Why did it come in here? It should do this and continue. Can I just print scene? Oh, I just saw my error. This should not be seen. This should be path. Yes, sir. Okay. Let's remove our print statements. And let's run it. This passes our tests. Wrong answer for 5. Return false, that you can't complete it even though you can. Okay, let's draw it up. Maybe my assumptions were wrong and I have to solve this problem in another way. Okay, so we have 1, 2, wait, there's 5, so it starts from 0 actually. 0, 1, 2, 3, 4. There's an edge from 1 to 4. There's an edge from 2 to 4. There's an edge from 3 to 1. There's an edge from 3 to 2. And that's it. So, is there a path where we visit the same node twice? Okay, we're gonna have to debug this a little bit. And we're just gonna add the same statements that we had before. You can't do this. Fine. Don't print scene. Where do we find the... Okay. So... we start at 0. It just visits 0 and then it's done. Then we go to 1. It goes 1, 4, and then it's out. So in our scene, there's currently 0, 1, and 4. Now in our 2, we visit 4 and then we're out. So now there's a 2 here. In our 3, we visit 3 and then 1, and then it exits. Why does it exit? Since it doesn't go out here, I assume... So it goes 3 and then 1. Did something not get cleared out of the path? Because I assume this is the part it counts, and then okay, I just did this twice. How did I do this twice? Oh my god, okay. $36K. GG. And then now we do this, Okay. Test it again. Ooh, we're running past our allotted time. I took too long to figure this out. Ooh, time limit exceeded. Let's see the constraints. What is the time efficiency of this? Time efficiency of this is you will visit every node, and for every node you're gonna visit every edge, every path. You're gonna go like this, you're gonna go like this. This node you're gonna visit, but you're not gonna do anything with it. How many nodes are there? Num cursors can be 2000. We don't really need to check nodes with no paths. Ibiza. The length of the prerequisites. This time limit exceeded here. Can we optimize? Okay, we don't need to run this DFS if we've already done the scene. Okay, so let's add that optimization. Or in here we have to make sure that, oh, I forgot. We have to make sure that we haven't seen this out node yet. So scene.count scene.count out node. So this is the first check to check if there's a loop. If this should be equal to 0. We should not have explored this node before. If we already explored that node, then we don't need to explore it again. I think that's the problem with our previous approach. Like, we do this check and balance here, that scene.count here, but we don't do it down here. Maybe this will fix it. Let's use this test case just in case. Okay. We made it to test case 52. Okay, that's better. What can we improve here? So I see something about like duplicate effort, and or like effort that's not needed, and that's if we don't really need to iterate over all nodes, because nodes that have no edges going into them like the edges that are not connected, that they're just like the one node, we don't need to check those. Okay, well, this is this is a problem with like the trade-off between being able to understand the problem, and I think, because I'm gonna try another approach, but I think this is a trade-off between trying to understand the problem and like the way I explained it, which might be a little bit easier to understand, and solving the problem in the most efficient way. So we're not solving the problem in the most efficient way because we're making it for ourselves easier to understand. However, we're losing some efficiency there, and we want to be as efficient as possible, so we're going to go into a harder approach. And that is, you know how we had this step right here of converting our Or what? We're converting our graph into an adjacency list. We can solve the problem without doing that, basically. But I feel like that shouldn't matter, shouldn't it? Okay, what if instead of a vector, like we do an adjacency list, but we're doing it differently? Because here we're already iterating over edges that have no what's I gonna say? That have no, we're iterating over nodes that have no edges. If we use an unordered map, we're just storing the edges that actually have we're storing the nodes that actually have edges. So we don't no longer need this. And here, if adjacent, so if adjacency list dot count of prereq 0 equal to 0, what are we gonna do then? We're gonna create it. So adjacency list of prereq 0 is gonna be equal to new vector int, and then we're gonna push back the other prerequisite. Adjacency list of prerequisite 0. Yeah, this stays the same. Now we're not gonna go over all num courses. We're just gonna go over all of the keys in adjacency list. So how do we do that? Const auto pair my map. Structure binding, ranges, traditional iterators. Okay, so we're just gonna do this. So here for const auto key value, or be I and value of our map, which is our adjacency list. Let's call it U and B. If scene.count U, and then replace this with U. And our adjacency list, it's gonna be an unordered map of int and vector of int. This would work the same. This would, yeah, that would work the same. Okay, let's see if this approach works. Let's include this test case and let's paste that in there. Okay. No viable overload equals. What do you mean? dereference it because we're passing a pointer instead of. Okay. If this doesn't work, we try making it more complicated, but for now, we'll see. This is a small optimization. We don't pass the previous test. Okay, I think this is the first time I've struggled with a problem. Memory limit exceeded. Okay. Do we think DFS maybe isn't the right way to solve this? Okay, what about BFS? You start, let's say, from here, then you visit this node, then you visit this node, then you come here, you visit this node, then you come here, you visit this node. How would that work in this case? Okay, maybe cycle detection in directed graph algorithms. Depth first search or cons algorithm via topological sorting. I know how to do a topological sorting, which is how I would have solved this, but I wanted to solve it via DFS. In the actual traversal path, which is V plus E. Okay. How about, I mean, how big is our, because I think just using the prerequisites, I really don't like this song. Just using like the prerequisites, if we want to find all the edges going outside from an edge, we'd have to look through this entire list basically. Unless we do, we can make this log n if we do binary search, I guess. That means log n every time we do it. So we do a trade-off between doing log n steps every time we explore a node, or just doing 5,000 once. Like I think 5,000 once is the, like, that should be fine. We should be fine to convert into an adjacency list. Whatever's taking us, like our time limit or whatever, that would have been something unrelated to this. Because doing this conversion from like the edge list to an adjacency list, it's basically O of E, which is the number of edges. So it would just be 5,000. So this process doesn't slow down the program. So where we're hitting the time limit is like this DFS. So there's gotta be a more efficient way to do it. I must be missing some like duplicate efforts. Actually, let me just copy this, and I think we can just paste this here, technically. And it would be the same. Same as, so instead of out node, and not DFS of adjacency list out node, U and path. We don't really need V. We can remove that. Here we're iterating over only nodes that have edges. Oh, okay. I found the problem. Let's do the same here. So the problem, and I think this is why we were hitting those issues with time, is that if you don't pass this as a pointer, every time this DFS is getting called, we're copying our whole adjacency list, which is O of E, of the amount of edges, or just this. We're copying the whole thing, which is yeah, basically just the O of V, of the amount of edges, which is crazy. That's crazy expensive. So we can't do that. We have to pass it as a pointer. Do I have to modify anything else in here? When we pass this adjacency list, we need to pass a pointer. Can I just... No, that dereferences it. So I need to pass the address. And same with path, I believe. And then same here and same here. Cannot bind to a temporary of type that. Oh, I think the way this is done, you don't actually need to do any of this. It does it automatically. Maybe. Yeah. Okay. Nah, I feel like now it's gonna pass. Oh my god. Okay. Let's explain the issue. So, and this is very important. I'm glad I noticed it. I probably would have done this in an interview, and this is an error. Okay, so our whole algorithm was right. There was one single problem, and the single problem is this. So the way functions work is for the STLs, like data structures like this, like a vector and an order map or whatever, is if you don't include this and, what you pass into the function is a copy of that whole thing. Every time, like, this is just how C++ functions work, don't ask me why. Every time you call this function with like this argument, so like when we pass this, like when we do DFS adjacency list right here, it's gonna pass a copy of this adjacency list. And that is a problem because that is very inefficient. Every time it's gonna make a copy how you would think of probably making a copy. So let's say, let's do it with this test case, right? You have this whole list of edges. How would you copy it? You would go one by one, and you would create a new vector, and one by one you would say push back this vector in there, push back this vector in there, push back this vector in that. And there can be a maximum of 5,000 of them, so that's 10 to the 3. So if we're doing that every time, like this algorithm is already like, I think we read it was O of V plus E, O of vertices plus edges, multiply that by edges again. So here you get O of VE plus E squared. And that is where all of our inefficiency is. And also, this creates a whole ton of memory that we don't need. Since we're copying it every time, every single call to this function has their own copy of that vector. So we're creating a lot of memory. So that's why you want to pass a reference to it. So we're reusing the same adjacency list. We're not creating a new one every time we call this function. Otherwise, the logic was fine. It's not the most efficient solution, but it works. I say 15 milliseconds. I'm sure if I run it again, maybe I'll get a better result. Let's try that, actually. Nope, it got a worse result. Fine, it passed. It passed. Okay, so that's good. We should move over to the next problem. Okay, let's put course schedule there. Implement try. Hopefully I can do a one shot of this. I'm very over my time, but it's fine. Okay, so 208, implement try. Prefix tree, a trie, pronounced as try, or prefix tree is a tree data structure used to efficiently store and retrieve keys in a data set of strings. There are various applications of this set of structures, such as autocomplete and spell checker. Implement the try class. Try initializes try object. Insert string word. It inserts a string word into the try. Search string word returns true if the string word is in the try, i.e. was inserted before, and false otherwise. Starts with, returns true if there's a previously inserted string word that has the prefix, and false otherwise. Okay, so let's look at a try to understand it. So it's gonna be similar to this, but we're not gonna have this 10, 10 or whatever. TTO. So, okay, we can put whatever we want in there. Object or search word, okay. Okay, so this is very simple. So how it works is it's a tree data structure. And so you want to see if there is a word that is in your tree. So how do we store words in our tree? So we're gonna have our root node is gonna be empty, because all of our strings, this is only for strings, right? All of our strings start with empty before you type anything, because we mentioned this is used for autocomplete. So it starts as empty. Then you start adding letters to it. So let's say we add to our dictionary of words, we add the word apple. What is that going to do? It's going to create some edges here. So it's going to create A, then P. Actually, this is the edge A, then the edge P would be now app. Then it would be APP because this is an edge P. Then this is APPL because this is edge L. And this is APPLE because this is edge E. Now let's insert the word apply. So instead of doing this again on like this side, we can reuse our path. So we already know we've inserted a word that starts with A, then goes P, so APP, then it goes L, APPL, and then it goes E, apple. This is where it differs between these two words. So we're gonna create another edge here with a Y, and that's gonna be apply, right? Then let's say like appetizer or whatever. Appetizer, you would follow the same thing until app, and then here would diverge E, and then T I Z E R. Now this is how it works to insert a word. Now we have two other operations, which is search and starts with. Search, we find if there is if we've inserted a word before that is exactly like that. So we go look for apple and we check how we inserted apple in our thing before. We go for apply, how we inserted apply. We could search like how we put in application. If we do a search of application, it's gonna say no because we haven't inserted that word before. And then starts with, it just checks if we've inserted that prefix into our tree before. So if we do that with like prefix, like starts with app, we go app, we have inserted before. Now there is a second part for like the search. We need to, when we're storing things, store a second value here that indicates we're gonna store it if there's a word that ends in here. So when we insert apple, we put end equals true, right? When we like this one, for example, appl would have end equals false because we haven't inserted the word nppl. So end equals false. Apply would have end equals true. So that way we know if we've inserted a word that's exactly like this. And this end equals false is going to help our search. Now we have to implement a tree. And this tree can have a lot of like subnodes. So actually, let me just copy this, and this is gonna go into our tree/208.cpp. So for our try class, we're gonna have try object new try object.insert word. Okay, we're gonna have a node class also. Class node, or yeah, that would node and leaf. No, we have leaf, internal nodes, and root node. Yeah, a node, and the node is gonna have that boolean we said before, where we check if the word ends in that letter, and then it's gonna have a vector of nodes, which is going to be called children. This is our whole node class. And the default constructor should already be included here, I believe, which just would initialize. Let's create a constructor, a default constructor. And this is gonna say, we do a constructor again. Okay, I need to brush up on my C++. Okay, value equals 0. Okay, so this is not actually how you do this. You do it like this. And then end equals false, and children equals vector of node, like that, I believe. And then like that. Just an empty vector. Okay. So when we initialize our try, when we initialize our trie, we're gonna say a node root is gonna be equal to node, like that. Let's use the new, so it gives us a pointer. New node. Okay, so a root is equal to a new node. So this is a root. It's just gonna be this empty part at the beginning. Then insert, we're gonna do the process that we talked about. So node cur equals root. Okay. So this can't be a vector. It has to be... Is this the right... okay. What are the letters they can use? Lowercase English letters. Okay. So at most 26. So we can use a vector of size 26. That's fine. Now, I like the unordered map better. Of char and node. This would be able to handle every single chart. Every single character, other like even outside of lowercase English letters. So we create cur, our root, and then for every character in our word, char C in word, what we're gonna do is cur children C is gonna be equal to a new node. Cur is gonna be equal to cur children C. And then at the end, we're gonna say cur end equals true. For search, what we're gonna do, we're looking for an exact match. So we're gonna walk down the tree with all of our letters until we get to the end. If we find a path that is not in our tree, that means our search is going to return false. So for example, if we try to look for stop, we go here, we don't find the nest, so that means it's definitely not in this. If we're looking for app, we go A, it's in the path, P is in the path, P is in the path, and then we check if end equals true. So search, we're gonna do very similar to this. Okay, we iterate over every character in the word. So here, if cur the children dot count C equals 0, so if the next character is not in our path, we're gonna return false. Otherwise, if it is, just move onto it, and then once we're done with our word, we return cur end. We check that is the end of a word. And then starts with is going to be the same process, but we just going to return true. Because we don't care if that is the end of a word, we just care that that prefix was in there at all. Okay, let's try the solution. No viable overloaded. Well, children. Ah, calling a private constructor of class node. Ah, these should all be public. We don't care about encapsulation. Use of an declared identifier root. Okay. So this is gonna be this root. No member named root in Trie. What do you mean? It's right here. Okay. Use of the declared identifier word. In line 41. Ah, prefix. Nice. Submit. Wrong answer. Okay. So, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. We're doing 1, 2, 3, 4, 5, 6, 7, 8, 9. We're doing a search of app. It should return true, but it returned false. Is app in? Did we insert app? We did insert app. When we're inserting. Oh, so we missed a part here. This is for doing it fast. When we're inserting, we don't create a new node every time because it's just overwriting every time. So we check first if there is a node. So if cur children dot count c is equal to 0, then we create a new node and then we navigate to it. If it's equal to 1, we just navigate to it. Use test case, run. Okay. Okay. Very sloppy today. I'm disappointed in myself. Okay, it took us a little bit longer today's stream because we had some issues. Okay, the first one. How bad do I feel about it? I don't feel that bad because it had nothing to do with my implementation, but it's something you need to be careful of. I hadn't encountered that issue in a while, so I'm happy I encountered it now so I can be more mindful in the future. but that is definitely very important when you find issues for your efficiency that are unrelated to your implementation. You need to be careful when you're writing code, especially that is a common issue of like using references instead of copying. That is something you should be mindful when you're writing code, because if I could have made that issue, like I could have made that same problem, that same mistake in at work on like a production code base, if I'm not paying enough attention. So it's important for me to take care of that stuff. And for the second one, I mean, the issues were kind of small, and it was because I was doing it fast. If I actually ran through my approach, I might have been able to find them before I submit it. So yeah, I think that's fine. It's a learning process. Like I mentioned, this is the first time I've actually struggled with any of these problems. We're on problem. What are we problem? What problem are we on? 26 right now. So they're gonna start to get harder. We're gonna have to get used to this. And we're gonna learn that's the whole point of this, to learn from our mistakes. So it's good. Okay. Let me write docs for this. So actually I'll write comments on the actual things. So n, here I'm gonna say n represents if we have inserted a word in the trie that ends in this exact letter. End will be false when we have inserted a word that contains the current prefix, but we have not inserted the current prefix as a word. I hope that makes sense. Actually, n will be true when we have inserted a word that is exactly the current prefix. Okay. This is fine. Insert. Check if the current letter is an existing prefix before creating a new node. Walk down the tree and create new nodes for new prefixes if needed. Mark the current word as existing in the trie. Walk down the tree. Actually, I'm just not going to include a thing there. If the current prefix is not on our trie, then the word is not on our trie. only return true on exact matches. Prefix exists, but is not necessarily a word in the trie. Okay. That feels satisfactory, and then we're gonna do 207. Okay. So writing here idea. Run DFS over graph to the okay. Actually, let's go from the beginning. We can express this as a graph problem. Every node is a course, and every edge is a every edge UV represents a prerequisite, where U is a prerequisite for course V, where course U is a prerequisite for course V. Our task is to find if there are any cycles in this graph. If so, it is not possible to complete all courses. To detect a cycle, we run the DFS algorithm while also noting the active path in our search. If we find a node and it's also in our active path, that means there is a cycle in our active path. Keep also a scene set so we don't explore nodes we've explored fully in the past. Okay. Convert list of edges to adjacency list. This is O of V. No, sorry, O of E. Run DFS on every node we have not previously explored. O of V plus E. I should look into why this is O of V plus E. Look into the explanation. I'll look into that in a second using Claude. And I'm gonna add here very important. I'm gonna add in all caps, very important. AG list and path should be passed as reference, not value. Otherwise, we are making a copy of both every time we call DFS. This is very inefficient and can make the solution TLE, time limit exceed. And then this is gonna be our backtracking step. Okay, that's good to me. Okay, let's try to think why it's all V plus E. You have all of your nodes, and then you do 1, 2, 3. What we're doing is, let's say it's a graph like this. In the worst case, we're starting here. Then yeah, okay, I see what it means, because you have to explore all nodes and then you have to explore all edges. So you go this, you explore this node, this, you explore this node, this, you explore this node. If there's if there's, it's V plus E and not just E, because if there's a disconnected node here, you could have all of them to be disconnected nodes actually. And if you're running DFS technically, and this problem doesn't matter, you can just be all of E, but technically you would visit every single one of these nodes as well. So it's all of B and plus E. That makes sense to me. I don't think I mean, let's, why is DFS cycle detection O of V plus E? Visits every vertex exactly once, and traverses every edge exactly once. The time spent processing is directly proportional to the numbers of nodes and connections on the edge. Yeah. That makes sense to me. And why can't we use BFS to find a graph? The first search is more memory efficient than the first search, and you can backtrack sooner. It's also prone call stack, but this relies on the longest path, not overflying. So I think you can do it BFS, but DFS is just more convenient. Okay, sounds good. Next time, ooh, have we solved coin change live? No, we have not solved coin change. I've solved coin change before. I have not solved it live. So actually, we're solving coin change next time. How we solve climbing stairs. Actually, this is not 27, not necessarily. This is 322. We have solved coin change before on stream. Okay, so that is checked. How we solve climbing stairs. 70. We have. Okay. Well, never mind. Okay, so all of the explanations are on the files. So we're just gonna push this. We're just gonna do git add period, git commit -m. Add solutions for the console logs. This would be 15. Push. Right, this is 15. Because tomorrow should be 16. Yeah, this is 15. Okay. Stick. We still have a lot of them to go, but we'll work through them. 169 problems. We're at 26. We're doing good. All right. Thank you guys for joining today. I appreciate you watching, and I'll see you tomorrow to continue building the RAG agent. Okay. Bye bye.